Hi, I'm Christopher Malon, and I am going to talk about how we can overcome poor word embeddings with word definitions. The problem we're addressing is that text classifiers can fail on unseen or rare words. A pre-2020 natural language inference model, XLNet trained on SNLI, misclassifies the premise John has COVID and the hypothesis John is sick as a neutral pair. We want a way to inject a definition, COVID is a respiratory disease, so that the model correctly concludes that John is sick is supported by John has COVID. To make a model that can use definitions, we need to make a training set of examples where those definitions matter. And the main idea we will use to do that will be to focus on what we call critical words. This idea is related to input marginalization, which quantifies the importance of a word by comparing the classification probability of the whole sequence to the classification probability conditioned on the sequence without the word. This decomposes as a sum of terms for each possible replacement word, where the probability of the replacement, which we get from the language model, is multiplied by the classification probability conditioned on the sequence with the replacement, which we get from the classifier. We will call a word critical if it appears exactly once in the example and there is a replacement that changes the most likely classification, and the replacement is at least 5% probable according to the language model. Here is an example. Our premise is a young man sits looking out of a train window, and our hypothesis is the man is in his room. This is a contradiction because he can't be on a train and in his room at once. Our language model has some probable replacements for train, namely side and small. And these alternatives make the example no longer be a contradiction, but neutral. So train is a critical word. To build a model that accepts definitions, we can keep the architecture, but enhance the training examples. We use Wiktionary as a source of definitions, using simple English if possible, and matching the part of speech, using the first definition listed without trying to match the sense. We take definitions of critical words in the training examples. We scramble the spelling of the word, so the model must rely on the definition rather than the word embedding. We append the definition to the example in the form word means definition, and then we balance the data set with a second example, where an alternative to the critical word is used that changes the classification. In this example, a blond man is drinking from a public fountain. The man is drinking water. Fountain is a critical word. We changed the original example by substituting a string of random letters for fountain and adding the definition, a natural source of water, a spring. The label is still entailment. We also add an alternate example where we use one of the alternatives for fountain, glass, and add its definition. Now we don't know what is in the glass, so the label becomes neutral. We apply this technique to enhance the SNLI training set, training on examples with scrambled hints and scrambled alternates. To get these examples, we need to have a critical word and find definitions for it and its replacement so that the training set is a bit smaller. We test in the same way, except we do not use the alternates because those labels are not verified. We base our experiments on the XNLI model, which gets 90.4% accuracy on the normal SNLI dataset. First of all, by scrambling the critical words, we have created a test that can't be solved well without reading the definitions. If we scrambled the words but don't give the definitions, the original SNLI model will get 54.1%. The model trained on our special training set will get an even lower accuracy because the bias towards the original word can't be used when the alternatives are present. Now, what if we provide definitions but don't provide a special training strategy and just add the definitions to the premises? Then the original SNLI model gets only 63.8%. Our special training strategy achieves 81.2%. This is close to the 85.1% that would be achieved if critical words were not scrambled. Thus, the definitions recover most of the performance that we lost by not being able to use the word embeddings. If we don't include alternatives to the critical words, the classifier learns biases that do not depend on the definitions. Trained on the verified examples without alternatives, the model without definitions can get 69.9%. If we add definitions but don't scramble the defined words, the classifier will use the original embedding and ignore the definitions. Such a classifier will perform well on the test set without scrambling, but won't know what to do when a new, i.e. scrambled word is encountered. We also investigated whether definitions were being memorized. Familiar definitions help a little bit, but we still outperform a plain SNLI model by a lot, even on definitions not seen in training. We also showed that definitions in the form of word substitutions of a familiar word were a lot easier than complex definitions. Unfortunately, we still don't know how to combine the benefits of definitions and word embeddings. We thought scrambling only half of the training examples would teach the model to do both, but performance on an unscrambled test set remains lower than if the definitions were not there. Finally, we tried to find naturally occurring examples with less common words in the SNLI test set. We considered examples where the lemma form of a critical word spanned multiple subwords. Because the whole word is not a subword, this means that it has somewhat lower frequency in the pre-training data of the language model. Indeed, these examples are harder, with performance of a normal SNLI model at about 77%. However, the word embeddings still perform better than the definitions on this set overall. In conclusion, we have introduced a method to enhance classification models to utilize definitions. This method fixes errors with new or unseen words like COVID. When a word is replaced by garbage, most of the performance lost is recovered when the definition is supplied. However, understanding of a definition is usually weaker than a well-modeled word embedding. Finally, our data set is available for download for further research. Thank you very much.